Hi everybody, welcome to Unit 2 of Geometry. We're going to be taking some notes here. We're going to start the first section off, but it's always good to introduce the whole unit. This unit is Reasoning and Proofs, or Logic and Proofs. Logic is how you think. You want to think logically. You want to make smart decisions and make things that make sense, that are reasonable. Thus, reasoning and proofs. We want to be able to prove what we think, and we want it to be a reasonable thought. Okay? Don't forget to put your name and hour on it. That way, if you lose it, it comes back to you. We're going to start off in chapter 2, section 1. Unit 2, section 1, called Inductive Reasoning. There's two different kinds of reasoning. Deductive reasoning, which is what Sherlock Holmes likes to do, and inductive reasoning, which is more an observation of patterns. And Sherlock will do a lot of this too. But inductive reasoning is making conclusions, or a conclusion, based on observations and patterns. So like if you look outside the window and you see somebody walking by in shorts and a tank top, and you see another person walk by in shorts and a tank top, and you see another person walk by in shorts and a tank top, you've observed a pattern. Everyone is wearing shorts and tank tops. So you can reasonably, through inductive reasoning, conclude that it must be hot outside. Because if you saw somebody walking by in pants, boots, a coat, scarf, and a beanie, and then another person do it, and then another person do it, and then another person do it, you could reason that it is cold outside. And that's inductive reasoning. Seeing a pattern that's happened so far, and then going a step further and saying, okay, this is going to keep happening. I can inductively reason this. When you come up with what is going to keep happening, that is called a conjecture. It is a concluding, or at the end, that is not the right letter, a concluding statement reached using inductive reasoning. Okay, so let's look at another example. Find the next 5 terms of the sequences, then write a conjecture. So here in example number 1, we've got 38, then 31, then 24, then 17, and we need to find the next 5. Well, if I look at that pattern, to get from 38 to 31, I went down 7. To get from 31 to 24, I went down 7. To get from 24 to 17, I went down 7. So I should just keep going down 7, which would be 10, and then 3, and then negative 4, and then negative 11, and then negative 18. And so then I can write a conjecture. To find the next term, subtract 7 from the previous term. That's all I have to do. So let's look at the next one. 2, 5, 11, 23. Let's see, from 2 to 5 is I add 6. No, that's not right. Let's see, from 2 to 5, I'm going to, I don't know, let's see what happens there. I'm going to add 3. And then from 5 to 11, I'm going to add 6. And from 11 to 23, let's see, I'm going to add 12. Oh, I see a pattern now. Look at this. Here we go. 3, 6, 12. 3 to 6 is double. 6 to 12 is double. So my next thing should be add 24, which would make that 47. And then my next thing would be to add 48, which would make that 95. And then my next one would be to add, let's see, 40, add 96. So 95 and 96, 180 plus 11 is 191. And then we're going to add 180 plus 12 is 172. So that makes a 316, 363. Is that right? I think that should be right. Let's see. 191 and 172. 191 plus 172 is 363. And then let's see, what is 172 times 2? I'm going to add 344. And so if I add 344, I get 707. Okay. Oh, let's see. Is that 172? Is that right? I don't think that's right. Let's look here. What is 96 times 2? Oh, 192. There we go. I was off by 20, which makes that 80. And then what's 192 times 2 is add 384. And so what's 383? Ooh, there's supposed to be an 8 in there. 383 plus 384 is 767. There we go. Look at that. Got to get the math right. There we go. Okay, so if we look at what happened as we went along, every time I moved up a term, I started with 3 and then doubled it each time. Is what I did. Now, I had to start by adding 3. And then I doubled it, and then I doubled it, and then I doubled it, and then I doubled it. And that looks like to be what is going on there. So let's see, how can we say that as a conjecture? How did we do 2 the first time? How did we pick 3 to get from 3 to 5? Well, we added it plus 1. And then we started to double. So to find the next term, always start it like that, and then we tell what to do. To find the next term, let's see. It started out with a 2, and then we added 2 plus 1, which makes 3. And then we added 5 plus 1, which makes 11. And then we added 11 plus 1, and then we added 23 plus 1. Oh, okay. So we're always adding the previous term and one more. To find the next term, add the previous term plus 1. Let's look at 3. 1, 4, 9, and 16. Let's see. 1, 4, 9, 16. What do we think needs to come next? Let's see. What's the difference between those? That's 3. Difference between those is 5. Difference between those is 7. Difference between those, well, I would say is going to be 9. What's the difference between 16, which would be 25? And then it would be 11, which is 36. And then it would be 13, which would be 49. And then it would be 15, which would be 64. And then it'd be 17, which is 81. All right, so all we're doing is adding the next odd number every time. But what else do you notice about those numbers? 1 and 4 and 9 and 16 and 25 and 36 and 49 and 64 and 81. Those are all squared things. 1 squared, and then 2 squared, and then 3 squared, and then 4 squared, and then 5 squared, and 6 squared. So to find the next term, how could we say to do that? Well, you could take whatever number of term it is, and the way that they can talk about that a lot of times is they call it the nth term. So if it's the first term, you replace n with 1. If it's the second term, you replace n with 2. If it's the third term, you replace n with 3. So we're going to take, I forgot the word take. We're going to square the nth term. So if it's the first term, you take 1 and you square it. If it's the second term, you take 2 and you square it. You could also say that each time you go to a next term, you add the next odd number. Okay. Or you're going to add 2 more than the previous term. Something like that. Okay. But these are all squares, so it's the square of the nth term. Sometimes finding these patterns is tough. It's hard to see patterns in the world, and you may not get it. But once you see it the first time, if you see it again, you'll be able to recognize it. All the more patterning. Let's look at number 4. A, D, G, J. Okay, letters. Well, let's see. What's missing? A, and then it goes B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y. Okay. So, to find the next term, let's see, count 2 letters. Ooh, that's supposed to be an L. From the previous. Or you could say skip 2 letters from the previous, something like that. Okay. Let's look at number 5. 2 more. 5, number 6. Let's look at 2 more. Okay. 7:30, 7:55, 8:20. So we got time now. From here to here is 25 minutes. From here to here is 25 minutes. So we should just keep going with that. That's going to be 8:45 when we add 20 and 25 minutes. And then we're going to add 25 more minutes. So if I add 5 minutes, that becomes 8:50. And if I add 20, that goes 9:10. If I add 25 more, that's 9:35. And if I add 25 more, that makes it 10 o'clock. And if I add 25 more, that's 10:25. Now, the tricky part with time is the minutes only go to 60, not 100. So, like when I added this 25 here, 15 of that gets me to 9 o'clock, and then there's 10 more minutes. And whenever I got to 9:35, 5 and 35 makes 40, plus 20 more makes the 60, which goes up another hour, up to the 10. And so, okay. So, to find the next term, add 25 minutes. Ooh, oh. U-G-E-S. Jesus, can't write. To the previous term. Now, let's look at this last one. This one may be a tough one. 31415. What comes next? Now, do you know anything that has 31415? know. I know that 3.14 is important. That's pi. Let's see what pi is. All right, if we just do pi and we push enter, 3.1415. Oh, look at that, match up. If we did 92653, we could plug in those extra pieces in there. Now, I cheated. I know a few digits of pi, so I can recognize that pattern. You may not know it, but this is what is called pi. Is approximately this, because we rounded it off. We didn't. It keeps going forever and ever. Okay, so to find the next term, how would we say that? Let's see. Each one of them is a place of pi. The first number is the first place. Second number is the second place. The third number is the third place. Let's see. So to find the next term, I don't even know what that is. The nth term is the nth digit of pi. Now that one's a hard one. You're not going to know that pattern. You're going to look at that and be like, okay, from 3 to 1, I went down 2, and then I went up 3, and then I went down 3, and then I went up 4, and then I went up 4 more, and then I went down 7, and then I went, like, there's no pattern to that other than you just have to recognize that it comes from something that already exists. It comes from pi. 3.141592653, blah, 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 keeps going forever and ever and ever. It doesn't stop. It's an irrational number. That one's a hard one. That one's a tricky one. But things like the time and the letters and some of these number patterns, especially the add and subtract ups, those should be things that we could do pretty good. Now, let's talk about counterexample. Okay. A counterexample is an example that shows a conjecture is false. An example that shows a conjecture is false. Basically, it's an argument to the conjecture, right? So whenever you make a statement, if there is something that you can say to disprove that statement or something you can show to disprove that statement, it is a counterexample. So let's look at these examples here and decide which one is true. That's what we're doing. Determine whether the conjecture is true or false. And if it's false, you should have a reason. You should be able to say it's false because of this. So like this first statement, the sum of any two consecutive integers is always odd. Well, consecutive integers is like whole numbers, but it could be positive or negative, but they have to be consecutive. It means one right after the other. So like 1 plus 2 is 3, and 3 plus 4 is 7, and 15 plus 16 is 31, and 102 plus 103 is 205. And the deal is with even numbers, you have to keep doing evens to stay even. As soon as you throw an odd piece on there, it's going to end up odd. So that is going to be a true statement. There are not two consecutive integers that you can add together in order to get something that's not an odd number. Now, if you added something like 2 plus 4 and you get 6, that's even, but those are not consecutive. We skipped over 3. So there isn't a counterexample for that. But now let's look at number 2. The product of two numbers is always larger than either number. And okay, we got to decipher what the words are. Product means we're going to multiply. So if we multiply two numbers, it's always bigger. Well, 2 times 3 equals 6. That's bigger. And 2, let's see, we can do another number. You can do 5 times 10 is 50. That's bigger. But what if you did 10 times 1/2? Right? That would be 5, which is not bigger, it's smaller. Remember, they said that they had to be two numbers. They didn't say they had to be integers. So if we use a fraction or a decimal, we're actually going to get smaller. So we could say false. I know that when I multiply 10 times 1/2, I get 5, which is actually smaller, right? So this is not a counterexample. That's not a counterexample. That's not a counterexample. That's not a counterexample. They all prove it. This is not a counterexample. That's not a counterexample. But that one is. It disproves the conjecture. The product of two perfect squares is always a perfect square. Well, let's see. We could do 4 times 9. That's 36. Interesting. Okay. We could do, let's see, 16 times 25. Let's see, what's 16 times 25? It's 400, and the square root of 400 is 20. So that's a perfect square. Now the deal with perfect squares is, like 16 is made up of a 4 squared and 25 is made up of a 5 squared. And so what that means is we have 4 times 5 squared. And so you're always going to end up with squared. It's that property of exponents that we looked at, where if two things are multiplying and have the same exponent number, you can pull that number outside a parenthesis. So this is going to be true, because you're always going to end up a squared thing when you multiply a perfect square times a perfect square. Now, number 4, if the area of a rectangle is 6 square meters, then the dimensions must be 2 meters by 3 meters. So whenever we're talking about area, it's length times width. So we need two numbers that multiply to be 6. Well, I can do 2 times 3, that equals 6, but that's what they said. It had to be 2 by 3. Well, it could be 3 by 2, but that means the same thing. What else multiplies to be 6? What about 1 times 6? 1 times 6 is 6. And so I could have a rectangle that is 2 by 3, or I could have a skinny rectangle that is 1 by 6. Both of those have an area of 6 square meters. So this would be false. And I've got a counterexample. It could be 1 by 6. Number 5. Dividing by 2 always produces a number less than the original number. Interesting. Well, let's see. 2 divided by 2 is 1. Okay. 10 divided by 2 is 5. Basically, we're cutting everything in half, and 5 is less than 10. Let's see. What's negative 4 divided by 2? Well, that'd be negative 2. Now, the weird thing here is that negative 4 is actually less, and this is more because it's less negative. So it actually produced a number that was more than the original number. So this would be false. And we could use negative 4 divided by 2 as our example. Number 6 says vertical angles are never complementary angles. Ooh, vertical means that they look like this, right? This angle and that angle. And never complementary. Complementary means that A plus B equals 90. They add to 90. So it says that vertical angles could never be complementary angles. Well, what adds to 90? Can the same number add to 90? Well, what's half of 90? Let's see. Half of 90 is 45. So if my vertical angle is 45 and it's 45, they're also complementary. So that is false. I could use 45 degrees. Let's look at 7. If A times B is 0, then either A or B is 0. Well, we know the rule. 0 times anything is 0. If it's not a 0, it would have to be a number. So the only way to get 0 on the other end is that one of them is 0. That is true. The only way to get a 0 is to multiply by a 0 when multiplying. If you multiply by anything else, you're going to end up with a number. Let's see, number 8. Two angles supplementary to the same angle must be congruent. Well, supplementary means that they add to be 180 degrees. So if I have two angles that are supplementary to the same angle, then they must be congruent. Would that be true? Well, supplementary means that it plus the other adds to 180. So if A plus B equals 180 and A plus C equals 180, if I move the A, then B must equal 180 minus A, and C must equal 180 minus A. And if they're equal to the same thing, then they must be equal to each other, because we can substitute. So I'm going to go true. Has to be the case. If they're both supplementary, they both add with that number to be 180, and if that number is set, they have to be the same number. So they have to be congruent. That makes sense. All state names have at least 2 syllables. Well, let's see. Start thinking of state names. Rhode Island is too many. Alabama, too many. Alaska, Arizona, Arkansas, Texas, that's closer. It's 2. New York, that's 2. Wyoming, California, Oregon, that's way too many. Washington's too many. Oh, man. Tennessee, Florida. Boy, a lot of them do. Is there a state that doesn't have 2 syllables? Vermont, New Jersey, Pennsylvania, Ohio. That one has 2. Minnesota, Montana, Dakotas. Seems like they all have at least 2. Ooh, what about Maine? That's 1 syllable, so I'm going to go with false. Don't forget about Maine up there in the upper right-hand corner. And number 10, squaring a number and adding 1 will always produce an even number. Well, 2 squared is 4, add 1 is 5. That's not an even number, so I'm going to go with false. Use the easiest one possible. Square the 2. So if you square an even, now if you square an odd number and adding 1, you would get an even most of the time. I can't think of one that doesn't do it. Let's see, 9's 81, it's odd, it's 82. Yeah, interesting. Okay, so you can't square any number and add 1 and get an even number, but if you square an odd number and add 1, you'll get an even number. Now take some time, write a couple of conjectures of your own, and then switch with somebody and see if they think that it's true or false. You can come up with any conjecture that you want at all. You know, you can say, I don't know, whatever you want to say. All birds fly. That's false. Penguins, emus, ostriches, they're all runners. They don't fly. So take some time, come up with them, and then see if your mom or dad can come up with a counterexample if you're at home, or if you're at school, grab a partner, see if they think it's true or false.